go ahead and get started. So our last speaker this afternoon is going to be Professor Ziyang Gao from Leibniz University of Hanover, and he is going to talk to us about rational points on curves.
Thank you. Thank you for the introduction. So today I will talk about sparsity of rational points on curves, and I'll list some known results and some open questions in the end. First of all, it's a fundamental question in math to solve equations, and here is the object that I will talk about in my talk. It's polynomial in two variables with coefficients in Q. And the question here is, what can we say about the Q solutions to this polynomial in two variables? This question is known as Diophantine problem, and it dates back to ancient Greek times. In modern language, it amounts to study rational points on algebraic curves. So this is fxy defined an algebraic curve, and the Q solutions are the rational points on these algebraic curves. Here are four examples. The first example has degree 2, the polynomial, and second and third examples have degree 3, and fourth example has degree 6. And the number of Q solutions are very different. In the first example, there are infinitely many solutions, and there are many, many small ones in the sense that both the numerator and the denominators are small. In the second example, there are only finitely many solutions. In the third example, still there are infinitely many solutions, but starting from the third solution, the numerator and the denominator are both very large. This is the difference between the first example. And in the fourth example, there are only finitely many solutions. The reason behind this behavior of having finitely many or infinitely many solutions, and when it has infinitely many solutions, whether we have a lot of small solutions or we don't have a lot of small solutions, they are determined by a geometric invariant associated to the curve defined by this polynomial. That is the genus 0, 1, 1, 2. And it fits into the philosophy of geometry governs arithmetic. So in my talk, I would talk about this according to the genus of the curve. Here are some notations which will be fixed in the talk. G and D will be integers, K as a number field of degree D, and C is a nice curve, irreducible, smooth, projective, of genus G defined over K. And as usual, we use CK to denote the set of K points on C. If you're not very familiar with this notation, then C is defined as the zeros of a system of polynomial equations, and CK is to say that C is defined over K means that we can find a system of polynomials with coefficients in K, and then CK is the set of K solutions to this system. When the genus is 0, the situation is rather simple. Either it has no rational points or is isomorphic to P1. So it has either no rational solution or it has many rational solutions, infinitely many and a lot of small ones. And better, we even have some local global principles here. And when G equals 1, already the situation gets a lot more interesting. Assume that we have at least one rational point. Then CK has an extra structure. It is an abelian group with an identity element in this as a rational point. So this pair of a curve of genus 1 over K and this distinguished element O, this pair is called an elliptic curve, E over K. Now, to study the structure of EK, first of all, it's an abelian group. So just by abstract theorem, structural theorem of abelian group, it has a torsion-free part, c to the power of rho for some rho, which a priori might be infinite, and the torsion part, which a priori could also be an infinite group. But then the theorem from Mordell-Weil says that, well, rho must be a finite number, and E tau is also a finite group, so it's finitely generated. Both parts are finite success. So in order to understand EK, we have two numbers to understand, two parts to understand, the torsion-free part, so the number rho, and the torsion part. For the torsion-free part, in general, there is no effective method to calculate, but here is a conjecture, the famous conjecture of Birch and Schwinton-Dyer, which says that rho can be computed using analytic methods. So it's the order of the L function at s equals 1. And in practice, sometimes we don't need something so specific. We need some upper bound for the rank, for the model rank. And here is an explicit upper bound. It depends on the elliptic curve in an explicit way, the conductor, and the field, C1 and C2. So C1 and C2 depend on K in an explicit way, means that it depends on the degree and the discriminant of the field. And a open question, a big open question is rho uniformly bounded for a fixed K? For example, when K is Q, some people believe that this rho will be uniformly bounded regardless of E, and some people don't believe it. And there are supporting evidence for both opinions. Okay, so this is for the torsion-free part. For the torsion part, the answer is fairly complete, especially when K equals Q. Mazur in 77 proved the following result, and then generalized by Camiani and in the end by Morel. They proved the uniform boundedness conjecture for rational torsion points on elliptic curves. It says that the cardinality of rational torsion points is uniformly bounded solely in terms of the degree of the number Q. When K equals Q, this is even completely explicit. Mazur gave a complete list of all the possibilities. To prove this result, actually, is quite interesting. Here we have a curve of genus 1. But what Mazur actually proved is a result on curves of higher genus. He showed that the only rational points of some modular curves, when n is large enough, are the rational cusps. And these modular curves, they usually have genus at least 2. So in order to study rational points on curves of genus 1, we are obliged to pass to higher genus curves to study that. And so now let's look at the case of higher genus curves. What happens? Well, a guiding result in this area is the Model conjecture, which was made about 100 years ago. It was proved by Faltings in 1983. The theorem says the theorem is really short. If the genus is these 2, then C has only finitely many rational points. So let's have a look at the theorem and first of all, the theorem is extremely strong because the hypothesis is really weak. It's just some weak topological hypothesis. The genus is at least 2. But the conclusion is about arithmetic. It says that there are only finitely many rational points. It's very strong arithmetic conclusion. So this makes the theorem really strong. And let's look at it, the theorem applied to Mazur's result on these curves when n is large enough. Immediately, it says that when n is large enough, then x1n has only finitely many rational points. So by Faltings' theorem. On the other hand, there is certainly room for improvement because no existing proof of Faltings' theorem is constructive, meaning that given the curve, we cannot determine the set of rational points using this theorem. For Mazur's result, Mazur really needs that x1n of q is just the set of rational cusps. So he really needs to completely determine this set. Well, Faltings' theorem or its proofs cannot. So so this is Faltings' theorem applied to Mazur's result. On the one hand, it is satisfactory. On the other hand, it cannot fully recover Mazur's result. And a more famous example in this feature is Fermat's law theorem. We have x to the power of n plus y to the power of n1 minus 1 equals 0, and this curve has genus at least 2, when n is at least 4. Applying Faltings, immediately we know that there are finitely many rational solutions to this polynomial. But for this example, more expected, we do expect that all the rational solutions are trivial in the sense that either x or y is 0. And This was proved only 12 years later by Wiles and Taylor-Wiles, known as Fermat's-Lac theorem, using the modularity. It's a completely different proof, independent from Faltings. Okay. Now, from this example, we see that given a curve, a simple curve like this, it's already extremely hard to compute the set of rational points. So this is really an extremely hard question to ask to compute the set of rational points. Instead, here is a more achievable but still fundamental question that we can ask and study. Is there an easy upper bound for the cardinality? And how do the rational points distribute on the curve? Where can we find them? And where should we not expect to find them? Guided by this question, I will talk about this question into different grades: finiteness, upper bound, a uniform upper bound, and effective results, effective model. Okay. Before moving on, let me introduce what the height function is. This is how when we try to list the set of solutions, we use height to order them, because height is a number to measure the size of rational and algebraic points. It's an appropriate generalization of absolute values for integers. First, on Q, any rational number can be written as a over b with ab coprime, and ab to be integers. And the height of this rational number is log max, the numerator and the denominator, the absolute value. So this is the height. So as soon as the numerator or the denominator is large, we say that this number is large. Okay? It suffices for one of them to be large. Next, on Pn of Q, yeah, it's very similar to the previous case. We just take a representative with coprime coordinates, and then the height is log max of all the absolute values. Next, for arbitrary number fields, we cannot get something as clean as this one because the class number is not necessarily 1. But still, we can write down the correct, the suitable generalization of this definition to number fields. We need to consider all the places. So even the height seemed a priori to be defined using only the Archimedean place, but in fact, it does contain some information of the non-Archimedean places also. And because this is arbitrary number field K, and it doesn't change under field extension because we do this normalization. From this one, we get the so-called logarithmic weight height on P to Pn Q bar, and then on any subvariety of X over X inside Pn. So why this function is called height? There are two very important properties of this for this function. Later on, we will see that we will define some functions on some varieties. We try to call them heights. But to say that they are actually heights, we need to check these properties. One of them is Knox-Gault property. One of them is bounded from below. So first, this height defined like this, obviously is bounded from below by 0. And secondly, it satisfies the Knox-Gault property. It's a finiteness result. It says that the number of algebraic points of bounded height and bounded degree is finite. There are only finite in many of them. So these two properties are very important to say that a function is a height. Especially this one, we often get finiteness from Knox-Gault property. Okay. Now, here is the finiteness of the result. It's proved by Faltings. And I extract this proof, this diagram from Statistical 127 by Lucien Spiegel. So we see that inside in this proof, actually Faltings proved a lot of big conjectures, Tate conjecture, Astronomic conjecture. And in the proof, he introduced something called Faltings height, which I will talk about later. But he proved it's almost like a formula for the height change under isogeny. Yeah, and so on. In the end, he proved a finiteness result for integral points on modular space. This is the Shavarevich conjecture. And then using the Godiva partition construction, this finite result of integral points on modular space induces what we want, finiteness of rational points on curves. So this proof is really a proof of integral points on modular spaces. And recently, there's a new approach to treat these kind of questions by Lawrence and Venkatesh. It also works in some cases for high-dimensional varieties. Okay, so this is the finiteness, Faltings' first proof. In this proof, we introduced this very important intrinsic invariant of an abelian variety, which we call nowadays Faltings height. Let A be a principally polarized abelian variety over Q bar. So Faltings define an intrinsic number H for A associated with A. You can see the definition either from a statistical or as Cornell-Silverman. Then we get a function from the modular space to the set of real numbers. So this is a priori a function. And then why is it called a height? Well, we need to check the two properties, bounded from below, not stopped. And Faltings proved this by comparing this Faltings height and the logarithmic Weil height, or any suitable logarithmic Weil height on the modular space. In the end, he proved that the Faltings height and its logarithm Weil height differs only from something log, because the singularity is a log. So because of this bound, because of this comparison, and this logarithm Weil height satisfies both properties easily by definition, so we get that Faltings height is bounded from below, and it satisfies the no-Scott property, so that it is indeed a height. But this height is very good in the sense that it's intrinsically defined. We don't need to put A into the modular space to define this number. It just depends on A. So it's an intrinsic number. Okay, now this is the first proof of Faltings. In my talk, I'll focus on the second proof of Mordell conjecture. This is a completely different proof given by Vojta. It uses Diophantine method. This proof is closer to Andre Weiss' whole. So he proved the Mordell-Weil theorem, which says that for any abelian variety, the set of rational points is finitely generated as a group. At first, he wanted to use this one to prove Mordell conjecture. Well, Faltings' first proof doesn't use it at all. But Vojta's proof is essentially depends on this Mordell-Weil theorem. This proof doesn't prove the other big conjectures like Tate conjecture and so on, but it also has its own advantage. For example, one sees some descriptions of the distribution algebraic points, and they will lead to nice upper bounds on the cardinality of rational points. And better, the proof can be used to prove some high-dimensional cases, the so-called Mordell-Long conjecture, based on this proof by Faltings. The starting point is to fix a rational point, even though sometimes it's the hardest step. But for Mordell conjecture, well, if we don't have any rational point, then the number of rational points is 0, so we have nothing to prove. So let's assume that there is a rational point, and then we use Abel-Jacobi embedding to put C into J. Now we see C as a subvariety of J. And if we take this point, the base point of a rational point, then CK is a subset of JK. Well, this is what we want to study. This is JK. It's larger a priori, but it has an extra structure. It is an abelian group of finitely generated abelian group. So it has more structures, and we have more tools to study. And here is the tool that we're going to use. It's called a normalized height function on the Jacobian. Here is the picture here. So first of all, we have this normalized height function. It is a height on the Jacobian to the set of non-negative real numbers. And we also know when where this height function vanishes precisely on the torsion points. And then we can restrict it to k rational points and then extend it linearly, real linearly. Then we get a quadratic form, which is positive definite. Pay attention, this positive definite is not given for free from the first part. Okay, we need to prove something, but it's true. So now we have JK tensor R. The Mordell-Weil theorem comes in this step. JK is a finitely generated group, so JK tensor R is a finite dimensional real vector space. Finite dimensional real vector space. And we have this positive definite quadratic form on it, H hat. If we take 1/2, the square root of that, we get a norm. So now we have a norm Euclidean space, JK tensor R, and this norm given by the height. And JK now, as a finitely generated group, it becomes a lattice in it. So JK here is all the dotted points. And among these dotted points, some of them come from CK. That's going to be the blue points and the red points. They are the points from C. And in the end, we want to study those the blue dotted points and red dotted points. But here we have a norm Euclidean space, so we can define inner product, angles, and so on. Now, let's see. First, let's go back to the 60s and see what Manteuffel already proved in this picture. He proved a formula which we now call Manteuffels formula. Here I'm writing down the consequence of that. If we have two algebraic points, distinct algebraic points coming from the curve, then we have some positivity. First, this leading term is a quadratic form, p squared plus q squared minus 2gpq. And then we have an arrow term, lower term, which is p plus q plus 1. It is non-negative. Now let's look at this leading term. When g is 0 or 1, this leading term is positive definite. But when g is at least 2, this leading term is indefinite. It's an indefinite quadratic form. And we know that an indefinite quadratic form, if we don't put any restriction from the source on the source, then it can take any negative value. It can take any value and as negative as possible a priori, if we don't put any constraints on P and Q. But this formula or this inequality says that, well, if P and Q are points on the curve, then no, it cannot be too negative. Cannot be too negative because it's a leading curve on something negative. So this already puts a strong constraint on the pair PQ on C. And this is one of the first evidences that algebraic points on curves of genus at least 2 are sparse. And here is the meaning. I think this is the wrong direction, but look at let's look at the picture over here. I merge Manteuffels inequality and Voigt's inequality in the same theorem. And everything is contained in this picture. Let's look at it. It says that we can divide all these lattice points into two parts. We are able to find an appropriate number, capital R, so that if we draw the ball centered at the origin of radius capital R and divide the points to large points, those lattice points norm at least R, and small points, those lattice points with norm at most R. Then if we focus on the large points, we have some sparsity results. We have large points which are close to each other with respect to the angle. This angle is R cosine 3/4. So if those large points are in the same cone defined by this angle, then they can not be too close to each other by Manteuffel. So if we have a P here, then Q, the norm of Q is at least twice the norm of P. So Q lies outside this part. And Voigt proved the converse. Well, Q also cannot be too far from P. They must lie within this part. Okay, now let's divide. This is a Euclidean space of finite dimension. So, and with this angle condition, we can divide it into finite number of cones according to the angle. And this number can be computed 7 to the power of the dimension, which is 7 to the power of the right. And restrict to each cone, we study the large points. then the number of large points can also be bounded. If we list the points here in the same cone as P, then by Voita, the norm of Pn as the most kappa times the norm of P. By manifold successively, the norm of Pn is at least 2 to the power of n times the norm of P. And then we can cancel out the norm of P here and get a bound on n. N is at most log 2 kappa, n plus 1 plus this P. So we have this many cones, 7 to the power of rank. And in each cone, we have at most log 2 kappa plus 1 large points. This gives an upper bound of the number of large points. It gives a finiteness, but better, it gives a large upper bound, which is solely in terms of G and the rank. Now, what happens to the small points? Well, if we are only interested in the finiteness, then we don't need to do anything. They are lattice points contained in a compact set, so automatically there are finite many of them. So that finishes actually the proof of Mordell conjecture if you can prove both inequalities. Okay, and now let's do a summary. So here we try to divide those lattice points into large points and small points. And we found this capital R. And even classically, it is known how R is what R is. R square is linear compared to the Fulton type. You see this very important term, Fulton type here. And the number of large points depends only on G and the rank of J. Yeah. So classically we get 7, but Levin-Alpogate improved 7 to something smaller than 2. Okay. So this is what classical is known already. And to get the bound of CK, we need to study also the small points. And by David-Philippon and Raymond, there is an upper bound, explicit upper bound, depending on 4 numbers: the genus, the degree, the Fulton height, and the rank. So far, we see that we have this degrees of question, the finiteness, the upper bound, we have both of them. And here is obtained by the sparsity of large points, manifold inequality and Voitas inequality. And then a natural question to ask is, okay, can we say something also about the small points? Can we get something better about small points to get some sort of bounds which are more uniform by this one than this one? And here is what we're going to look for. Now, before trying to prove any uniform bounds, let's see how uniform can any reasonable bound be. Here are 2 examples which tells us that, well, it must depend on the genus and the degree of the number field. And then a very ambitious question is, are these 2 numbers suffice enough to bound the number of rational points? This question has an affirmative answer if one assumes a widely open conjecture of Bombieri law on rational points on variety of general type. This conjecture itself has divergent opinions on it. This is proved by Cabralza, Harris, Maser with K over Q replaced by just a number field, and then improved by Abramovich and Bacelli to this form. Okay. There are 2 divergent opinions on this conditional results written here. Okay, so this is a very ambitious bound. Instead, here is a bound which can be proved, which is more uniform than the classical bound. The number of rational points is bounded above solely in terms of the genus, the degree of the number field, and the Mordell rank. So compared to the classical bound, the Fulton height is no longer in the constant. And Kuhne improved this bound by removing K over Q in the constant. But K over Q will always appear in the Mordell rank anyway. Yeah. And previously, some results in this direction are proved by different people. When J is a subvariety of e to the power to some power of elliptic curves, it was proved by David-Philippon, Nakamaye, and Levin-Alpogate proved the average number of genus 2 curves. Not something as strong as this one, but he proved that the average number is a finite number. So this proof is based on the Dufresne method. So Voigt has proof that I explained before. Another sort of results in this flavor is by Chabauty-Coleman method. So this method works when the rank is small. In the hyperelliptic case, it was proved by Michael Stowe, and then this result was generalized by Kasparov, Brown to any curve of small rank. Okay. Here is an example. A one-parameter family of genus 2 hyperelliptic curves, and in the end, the number of rational points is bounded above subpolynomially. This example is a bit particular because the Jacobian has rational two torsions. So the rank is easily bounded in terms of S. Okay. Now, how do we prove this rather uniform bound? Well, we established this by proving a result which says a bit more about how the rational points, how points are far from each other. Actually, it's algebraic points from each other. The result is as follows. So if G is at least 2, then around each algebraic point, there are only finitely many other algebraic points which are not far from it in a rather uniform way. Here is what it means. Not far means the height or the distance, the square of the distance, is bounded above by linearly in terms of the fault's height. This is what not far means. And then the number of these points is bounded above solely in terms of the genus. And this result is a combination of two results. So with Dimitrov and Pabeger, we prove it for large curves, which suffices to prove this rather uniform bound with K over Q. And Kuhne proved this result for small curves. So you really combine these two results to get it for all curves. Again, our proof doesn't come from nowhere, or this result doesn't come from nowhere. It is an explicit, a quantitative and uniform version of the Bogomolov conjecture proved by Yunmo and Shou Zhang. So Yunmo proved this result with C1, C2 completely unknown, and depending on C and P, in a completely unknown way. Shou Zhang proved this result with C1 and C2 depending on C in a completely unknown way. Where we don't even know what geometric invariant they depend on. But still, their results already says that these algebraic points should be sparse from each other in a non-uniform way. We prove it in this quantitative way. We and show how uniform it is, how uniform it can be. And it is a quantitative way to say that algebraic points are really sparse. They're far from each other in terms of the distance. And let's see how this theorem proves this rather uniform bound. It's quite easy by the elementary packing argument. Let me explain it. We only need to prove it for small points because the bound of large points is already good enough by classical results. Now, what are small points? They are points of norm at most capital R. And now let's try to cover this large ball by small balls of radius small r, with r squared being this term. And how many small balls do we need to cover this large ball? This is an easy calculation. Is capital R over small r to the power of the dimension of the space. Okay? And in this quotient, in this ratio, the height is cancelled out. So this number depends only on G. And then you have the modality rank. And next, in each such small ball, the number of points is at most C2, which is a number depending only on G. So you multiply both of them, you get the bound, the desired bound for small points. And then we're done. So let me make a summary. So here we have a rather uniform bound on the number of rational points. And to get it, we prove some new gap principle to say that algebraic points are sparse from each other, also small points. And then effective modal, what it is? Well, it is almost the ultimate goal that we want to realize when studying algebraic rational points on curves. Um, so the statement, the slogan here is there are no large rational points. And the correct statement, the exact statement, is this conjecture made by Spiegel. It says that there exists an effectively computable constant depending only on the genus and the number field, such that all rational points are small points. And by explicitly effectively computable, depending on the number of fields, I mean it depends on the two simplest invariant of the number field, the degree and the discriminant. So effective model tells us where to find those rational points. There are no large rational points. All of them are small. So if you can prove this one, then you can plug in and get an algorithm for each curve to have all these points. But I say that it's almost the ultimate goal because even you prove this one, you can't get Fermat's theorem immediately because Fermat's theorem, there are infinitely many curves. You have infinitely many n. And again, very, very little is known about the effective model. There are some results proved by Gregoli, Veneziano, and Yada, but only when C is contained in e to the power of n and n with small rank, following the method of Manning and Damianco. Okay. So another way to study or find rational points on these curves are the Chabot-Coleman-Kim method, which let me shortly explain what it does. Well, it's by obtaining sharp bounds on the canality when the rank is small. Why do we need the rank to be small? Here, let me explain this. The classical Chabot-Coleman applies when K is Q and JK has rank smaller than G. Because here is what we do. We have this set CQ inside JQ, but then we take a prime number P to put CQ into CQP. All of them will be in JQP with a p-adic variety. Now, CQ is in the intersection of CQP and JQ, even the closure of JQ. Now, it can be computed that the dimension of the closure is bounded by the rank. This is where we use P. You can't work it over Archimedean place. And if it is smaller than G, then the dimension here is smaller than G. So here you have something of dimension G, here you have something of dimension smaller than G, you have something of dimension 1. They are unlikely to intersect. And the intersection will be a finite set. And CQ is inside this finite set. So this is how we get finiteness. And this approach can be made into effective by Coleman. Okay, so this is why we need the rank to be small. Right. This is also how people can prove the finiteness of rational points when the rank is small. Quadratic Chabot goes some steps further and applies to some cases when the rank is G and when the curve has a lot of correspondences. So it works well for modular curves, for example, in various publications of Jennifer Balakrishnan with her collaborators. Besser, Mueller, Dogba, Yang Wang, Tweetman. So here the idea is we see now the constraint on the rank is because this dimension of this variety, the large ambient space is G. If we can enlarge this ambient space, then we may allow some more rooms for the rank. And here is how to enlarge this J, the JQP, the geometric point of view by Edison and Lido. So here we have the Jacobian, and we put the Jacobian we map the Jacobian to Jacobian times its dual. On this one, we have the natural Poincare tensor, GM tensor. It's a GM tensor on this one, and we can try to pull back using endomorphisms of J. So if we get a pullback, then here we get one more dimension. There's an extra GM in the dimension. And then what we want to do is, okay, C naturally lives in J, but does C lift to that? So this is the question. And the condition for such a lifting to exist is exactly that the degree of the pullback restricted to C, here is the restricted C, is 0. And then how many Fs do we have here? Well, it's the number of the rank of the Nihon symmetry group minus 1. So if the Jacobian has large Nihon symmetry group, then we allow this rank to be smaller than something larger than G. Okay. So this is what happens. Okay. Now, okay, I have 5 minutes. I guess I don't want to say too much. Then I'll just skip most of the slides here. This is about the quick summary of the proof. The proof has 2 steps. We want to compare 2 heights. So if you look at this result, here is a height on the Jacobian. Here is the height of the Jacobian. We want to compare the 2 heights. And we put everything together into a family. A priori, there's no reason that a height fiber-wise defined here and a height completely on the base can be compared. A priori, there's no reason for that. And what we want to do is to find the correct condition on the subvariety so that these 2 heights are comparable when restricted to this subvariety. We want to find the correct condition. And this correct condition is called non-degenerate. And in the recent terminology of Yuan and Zhang, it's equivalent to say that topological identical line bundle is big when restricted to X. So it's a bigness of some line bundle. And to prove, to construct an appropriate X or prove that this line bundle is big on X, we prove this kind of criterion. For this purpose, I introduced this degeneracy loci, and using the mixed X-Chanyu theorem, I gave a criterion for this non-degeneracy. This non-degeneracy amounts to say that anything non-degenerate comes from something naive non-degenerate. Anything degenerate comes from something naive degenerate, even though the full statement is a bit complicated. And using this criterion, this theorem, one can construct the non-degenerate subvarieties to work with. For example, for this, for the rational points on curves that I talked before, it's this variety is used, and later on with Tangli Ge and Lars Kuhne, we generalize this construction using Hilbert schemes and so on to prove the full uniform Model-Lang conjecture. And more recently with Habegger, we proved the so-called relative many-manifold conjecture, which is about algebraic torsion points on families of abelian varieties. It basically implies all results on algebraic torsion points on families of abelian varieties. And here we need to go one step further, use some sort of X1, which is one step further here. Okay, here are some applications. All right, now I want to talk about some open questions here. We see that this is the rather uniform bound we proved. Here you have a C2, which is the number of points in this ball. And then you have the CG, which is capital R over small r. The C2 is usually called Manning-Manifold constant, and CG is called Loita constant. The Manning-Manifold constant, first of all, it must grow to infinity, because you see this example, it must grow to infinity. Over function fields, it is proved that it's comparable to G square by Looper, Silverman, and Rose. So it's a natural question to ask, okay, over number fields, how does this Manning-Manifold constant look like? Is it also G square? It is not known. There's even no explicit formula. Next, if we confine ourselves to rational torsion points, can we say something more? Rational torsion points or torsion points. Can we say something more? Here is a uniform result of Baker and Poonen. They prove that the torsion packet here has cardinality at most 2 for all but finitely many points for any individual curve. But here the constant, again, depends on the curve in a completely unknown way. We don't know which geometric invariant it depends on. And a natural question to ask is, can we make Baker and Poonen's result uniform? So is it possible to make this BC uniform in G, but maybe at the cost of replacing 2 by something larger? Okay. This is for the many-manifold constant. And for the Volta constant, we actually expect CG, the Volta constant, to tend to 1 when G goes to infinity. Okay, I'll stop here.
Okay, so this effective model is very far.
Yeah.
Suppose I know this one solution,
Still, yeah,
and the
well,
other solutions be found in terms of.
yeah, well, if you know one large solution, yes. Yeah, I mean, if you know one large solution, then in this cone, you know where to find all the rest. But yeah, this is often the problem for effectiveness. You don't know where to find a solution. And all proofs of model has this problem. You don't know where to find a solution like that.
So going back, if I take a rational point.
Yeah.
And when I adjust the coefficient of the equation so that it's a perfect contained function.
Yeah.
So we can create examples where.
Well, the thing is still you need a base point. So you need this P to be sort of this large point. Yeah. So one is the base point and one is another large point. Yeah.
Some example.
Yes, well, it is the man in the Blanco. It's the rank of the automorphism compared to.
Any other questions?
Yeah.
This Baker-Poonen problem that you mentioned. So
yeah. Ah. Yeah.
So actually, one question I had is why do you think 6 is the correct constant?
Yeah. So this is actually an interesting question. So we sort of think about this because after we prove relative many-manifold, uniform many-manifold is an easy consequence of relative many-manifold. And in the proof, we also need to go to this fiber products. Actually, Michel Stowe also did this before we did that. So somehow we need to go to the 5th or 6th power, depending on how you see this. Yeah, because it's the 6th power, so we guess that probably 6 is the correct number. It's by the somehow the proof. Yeah, uniform many-manifold is proved by last Pina. We sort of give a third proof. Oh yeah, I should have mentioned that for this new gap principle, Xin Yuan gave a second proof to that completely independent proof.
Hey, any other questions? Okay, let's thank our speaker again.